Covalent chemical bonds. What is a chemical bond? Well, a chemical bond can be viewed as forces that cause a group of atoms to behave as a unit. All right, so why do chemical bonds occur? Bonds result from the tendency of a system to seek the lowest possible energy. Atoms that function together as a group are called bonded. And we talked about the fact that there are three types of bonds that we're dealing with: ionic bonds, covalent bonds, or polar covalent bonds. So here's an illustration that helps us to determine the difference between ionic, covalent, and polar covalent bonds. On the top, we're looking at two atoms that are equally sharing a pair of electrons between them. So that would be an example of a non-polar covalent bond, which is sometimes referred to just as a covalent bond. In the middle, we're looking at two atoms that have differences in electronegativity. The atom on the right-hand side has a higher electronegativity than the atom on the left-hand side. Still not great enough to take electrons away. These two atoms have to share pairs of electrons, but they're not going to share them equally between them. The more electronegative element on the right is going to have a greater attraction for the pair of electrons in that bond than the atom on the left, so that will give us a partial positive and partial negative side to our molecule, or the molecule will have a dipole moment. Now, if there's a big enough difference in electronegativity, like we see in the bottom example, the atom on the right-hand side has a very high electronegativity relative to the atom on the left-hand side, so electrons are going to be transferred from the atom on the left to the atom on the right, and because of that transfer of electrons, we're going to be left with ions. A positively charged ion on the left because we've lost electrons, and negatively charged ion on the right because we gain electrons, and the attraction between unlike charges is what will hold those ions together in that ionic compound. So we want to talk about covalent bond energies in this particular section. So we know that we can determine the energy of a particular chemical bond by breaking it. We have to add energy in. So the question, are all carbon-hydrogen bonds the same? So let's look at an example. Let's say that we've got this molecule here, CH4, which is also referred to as methane. Each of those carbon-hydrogen bonds is a covalent bond. So we're going to stepwise break a carbon-hydrogen bond and measure the energy associated with it. So we're going to take methane and remove the first hydrogen, and we have to add in 435 kilojoules of energy per mole to do that. Now we're going to take that CH3 particle and remove another hydrogen. We have to add in 453. Now we're going to take that CH2 and remove another hydrogen, 425. And finally, we've got that CH left, and we'll break that bond, and it's 339. Now let's notice that each of those values is a positive value because we have to add energy in order to break bonds. But they're not all the same value. If we were to add them all together, the total amount of energy that would have to be added in to break all four of those bonds is 1,652 kilojoules per mole. So what do we know about carbon-hydrogen bonds? They're not all the same. But what we can do is we can average those four values together. Take that 1652 divided by 4, and we're going to get an average bond energy of 413. The energy varies in a non-systematic way when we break each of those hydrogen-carbon bonds because the carbon-hydrogen bond is very sensitive to the bonds that are around it or to its environment. It varies because the electronegativities of the other atoms in the compound. So is it okay to come up with average bond energies? Although the bond strength varies, the concept of the average bond strength is still useful to chemists. So we have three types of polar covalent bonds that we want to talk about. Bonds where a single pair of electrons are shared is called a single bond. When two pairs of electrons are shared, we'll call it a double bond. So a bond where three electrons are being shared would be a triple bond. I knew you'd catch on. So bond length is the distance between two covalently bonded atoms. The more electrons that are shared, the shorter the bond length. So a single bond is longer than a double bond, and a double bond is longer than a triple bond. So let's look at bond energies and enthalpy changes for reactions. We can use bond energies to calculate the approximate energies for reactions. There are two basic things that have to happen in order for a reaction to take place. For a reaction to take place, the first thing we have to do is break the existing bonds that are holding the atoms together on the reactant side of the reaction. And breaking bonds is an endothermic process because we have to add energy in. Now once those bonds are broken, the atoms are going to rearrange themselves, and then we must form new bonds to hold the atoms in their new arrangement on the product side. And forming bonds is an exothermic process, or it releases energy. So to find the enthalpy change for a particular reaction, what we're going to do is we're going to take the sum of the bonds that are broken. We're going to subtract it from the sum of the bond energies that are formed, and that'll give us the energy for the particular reaction. Now, bond energies are things we can look up on tables. They're always going to be positive because bond energies are written with respect to breaking bonds. But if we look at this equation, we're taking bonds broken and subtracting bonds formed. By subtracting this value, in essence, we're changing the sign on the bonds being formed, and we're making it exothermic. So the enthalpy change for a particular reaction is the sum of the reactants minus the sum of the products, or the sum of the bond energies for the atoms or the bonds that are broken minus the sum of the bond energies for the bonds that are formed. The keys to success. The first thing we have to do is we have to figure out all of the bonds that are broken, and then we have to figure out all of the bonds that are formed. So we'll start with a simple example. Let's say that we've got the diatomic molecule hydrogen, so that's an H with a single bond to another H. And we've got the diatomic molecule fluorine, which is a fluorine single bonded to another fluorine. And we're going to go through a synthesis reaction to make hydrogen fluoride gas, which is a single bond between the hydrogen and the fluorine. But in the balanced equation, we're going to end up with 2 moles of hydrogen fluoride gas for every 1 mole of hydrogen and fluorine that we start with. So we're going to use a chart that gives us covalent bond energies and our equation for calculating the enthalpy of a reaction using bond energies to calculate the energy for this reaction. So we have to figure out what bonds are broken first. Well, we're going to have to break the bonds that are holding the atoms together on the reactant side. So we're going to have to break a hydrogen-hydrogen bond, and we're going to have to break a fluorine-fluorine bond. Next, we have to figure out what bonds are formed. Well, we're going to have to form a bond between hydrogen and fluorine to form our molecule, but there are 2 of them. So there's actually 2 HF bonds that need to be formed. So now that we've determined that, we're going to take our equation. We're going to take the sum of the bond energies for breaking our bonds. subtract the sum of the bond energies for the formations of our new bonds, and that'll give us the enthalpy for the reaction. So we look on our table, and it tells us that the bond energy for a hydrogen-hydrogen bond is 432. That's how much energy has to be added in to break that bond. The bond energy for fluorine-fluorine is 154. That's the amount of energy per mole of fluorine-fluorine bonds that we're breaking. We'll add those together. And then 565 is the bond energy for the breaking of a hydrogen-fluorine bond. But we've got two of them, so we're going to multiply that value by 2. And we're not breaking that bond, we're making it, so we're going to subtract that value, which in essence changes our sign. And what we find out is the enthalpy for this particular reaction is negative 544 kilojoules of energy.